established already that that work is, oops, let's get the right layer here. There we go. Work is force times distance. It's force expended over a certain distance, over a, I want to say displacement, but it's not displacement. It's very similar to that, but it's distance. It's simply a scalar quantity. It's one direction. It's not positive or negative. It's just distance. But also times the cosine of this symbol that we call phi. Now, phi is simply the angle between the force and the displacement. For example, the picture right here, our diagram. Here's our displacement, right there in blue, and our force is right here. Now, in this case, the force is at more than a 90-degree angle away from it. It's at, looks like 160, 170 degrees, which means it's going to be negative work. But regardless, this is the angle between the force and the displacement. The other possible angle would be this angle right here, which we're not going to measure. Phi is always the smaller angle between the force and the displacement. But in this case, oops, I got rid of my, there we go. In this case, phi is actually happens to be larger than 90 degrees, which brings us to the idea of negative work. If you have a force right here, here's our force, and it's in a different direction than the direction of displacement, or it's a predominantly different direction, we call that negative work. That happens only if phi, that is the angle between the smaller angle between the force and the displacement, is greater than 90 but less than 180 degrees. Most of us don't actually exert a force in a given direction and have us be displaced in the opposite direction. But if you think about it, when we exert a force in one direction, what force oftentimes opposes us? Well, that's friction. So friction, you could think of it as doing work against us. That's the way we can think about negative work right here. So negative work. Well, we all can also have the concept of net work. Of course, not network. We're used to hearing network as in, a network of computers. No, this is simply net. That is the net of all the works put together, the total work. And it's summed just the same way that the net force would be summed together by adding all the forces. And then we put a sigma in front of it. That means the sum of or the sum total of. We just add them all up, and then that's our net force, or in this case, it's our net work. Now, these works can be in different directions. Like I said just a minute ago here, if we're exerting a force, let's go. Here's our work force, work of me, okay, going in that direction. Friction will be at odds at me, and so it will be kind of in the negative direction to the force that I'm trying to exert. But that's how we add them together. We add all the forces together that are in one direction. We subtract forces that are going in the opposite direction. And we have our ultimate net work right here. So let's actually do a problem that illustrates that. And up to this point, I've had a lot of extra space right here, but we're gonna use it right now. We've got a car, and I think this is the one that Mr. Knickerbocker, your sub, who, as I understand it, was a very, very good sub, very knowledgeable in physics. I think he bypassed this because, well, I'm not sure the reasoning he thought, but I can imagine it's because there's no actual numbers in it, that he wanted to give you something with numbers. But we'll just add up the net work, and should be the total work. Total work is kind of the same thing as the net work, but we're going to add them up regardless, even though we don't have any numbers. So here's our car right here. And in fact, I'm going to make that black wheels. Okay, and a red car. Whoops, my pen is a little inaccurate today. Okay, there's a car to go down the road. And we've got a couple different forces. We have the normal force. That's this right here. Now, we've notated it as just a capital N. But F sub N is very common as well. We have the force of the air. Now, if you think about it, what kind of force would air exert? Well, it would be resistance force. You might say friction force. Okay, so that gives us an idea of how to draw that. And then we have the force by gravity, which we call mg. So let's label these all on here. mg right there. And mg is broken into two parts, remember, because we have a hill right here. By the way, this is our angle theta that the hill is angled at. And mg is broken into two parts. We have the perpendicular to the surface, which is mg cosine theta. And then we have the parallel to the surface, mg sine theta. Okay, so that's our weight force broken into two parts. Absolutely appearing to have some sort of effect on the car going down the hill. But these other forces, how do we figure them into play? Well, we have our force of the air, which we have right here. Well, that's friction. That acts against the motion of your car, against the force causing your car to move. So we're going to draw that in the opposite direction. That is, it looks like fair. F air, that's the force caused by the air, the friction force caused by the air. And then, of course, there's the normal force, which we just notate as a capital N, just like that. Okay, so the question is, what is the total work done on the car? By the way, we have one more thing to draw in here. Here is our D, our displacement. So the car is being displaced down the hill, parallel to the surface of the hill, right there. Okay. Well, let's see. What's the first force that's listed here? Well, I don't want to do normal force yet. Let's start with our weight force. What force is created? I'm sorry. What work is done by our weight force? Okay, well, the weight force right here, mg, is directed mostly into the hill, but part of it is directed downhill, and so our force, we've been calling this force parallel, is moving the car down the hill. And think about it for a minute. What does the force perpendicular actually wind up do to the car? Does it do any work on the car? And the answer is no. It doesn't, because it's not moving the car into the hill. Really, the only component of the car's weight is moving it down the hill. So the car, I'll say W, let's draw that in black. Work of the, not the work of the car, right? The work done by gravity on the car, right? Work done by gravity. mg is what? Well, I'll tell you what. Let's just refresh real quick. What is our equation for work? That would be work equals force times distance times a cosine of the smaller angle between that force and the direction of motion. All right. Well, in this case, we've already broken mg into a perpendicular and parallel component, and the parallel component is in the direction of motion. This parallel component right here, is there any angle between that and the displacement? No, they're parallel to each other. They're on the same, you might say they're on the same plane. So our weight done by our work done by our gravity would be mg sine theta, that's our downhill force, times d, our displacement. That would be the work done by our by the downhill component of our weight. All right. Well, then, what work is done by the force of the air? Work done by the air acting against the motion. Well, if this angle right in here, we'll call that phi for now. That angle between the parallel force and the road surface is 0. All right, then that means that this angle, just like that whole angle that is between the direction of displacement and this air friction force right here is what? Well, if that's 0, then this all the way over here is 180. So the work done by the air would be the force of the air times the displacement times cosine of phi, which in this case would be 180. FAR times our displacement times a cosine of 180 degrees. Which, by the way, I forgot to write this up here. For the work done by gravity, cosine of 0 degrees. Well, what is that? Well, that's 1. The cosine of 0 is 1, so it doesn't change anything. But this right here, how would the work done by the air be different from the work done by the parallel component of gravity? Well, it would be 180 degrees in the opposite direction, or that is, it would be negative. We'd have a negative work done by the air. Here's a great example of negative work done on the car. Okay, well then we have those two. And now let's write the work done by the normal force. There we go. Work done by the normal force right here. Well, the normal force is, you know what, I'm going to erase that. Normal force is the same thing as what? Well, it's normal force in this case is the same thing as the perpendicular force right here. Remember, these guys and these guys are both the same thing. They're just in opposite directions. But so that would be mg cosine of theta times d, our displacement, times a cosine of what? What's the angle between either our normal force or our perpendicular force and the direction of displacement? What is that angle? Well, it's 90 degrees. Cosine of 90 degrees. Which, if you think about it, that equals 0. So the perpendicular component of the car's weight directed into the road, and the same thing as the normal force, that is the road supporting that weight, both of those do absolutely 0 work on the car because they're not contributing towards its direction of displacement. They're at right angles to it. And that 90-degree right angle results in 0 work being done. So let's add all these up and we'll have a statement that expresses the net work done on this car. Net work would be mg times sine of theta times our displacement times cosine of 0, which isn't really necessary, but we'll write it in, plus the air force or friction force times displacement times the cosine of 180 plus, and I just ran out of room. You know what? I'm going to just copy. I'm just going to, oops. Let's do that again. Let's move all that over. Make a little more room for myself there. There we go. Okay, and our last one is plus our normal force. That is n times our distance or displacement times a cosine of 90. That should about do it for this part. I think I'm almost out of my 15-minute time, so I'll look for you on the next one. We're going to pick up, once again, talking a little bit more about net work. I'll see you then.